corollary is to say that if a series of complex numbers converges, then nth term converges to 0 as n tends to infinity. Okay? So this is kind of criteria if we can check whether a given series diverge or not. We just check the first, the nth term. If nth term converges to 0 as n tends to infinity. Okay, let's see the proof. Assuming that series 1 here, summation n is equal to 1 to infinity gn converges. We know from the theorem that if gn is written by xn plus I yn, then each of the series, this series comes from real part in the series 1. Then this series comes from imaginary part from in series 1 converges. We know moreover from calculus that nth term of convergence series of real numbers approaches 0 and as n goes to infinity by the theorem in section 60. So we consider a limit n goes to infinity gn, then which is equal to gn is equal to xn plus I yn. Then limits can be applied each term. So limit n goes to infinity xn plus I limit n goes to infinity yn. Both sides goes to 0 by the assumption. Just we checked before. So the proof of corollary 1 is complete. It follows from this corollary that the terms of convergent series are bounded. This fact will be used for our main theorem of this time. That is, when series 1 converges, there exists a positive constant m, large M, such that absolute value of g sub n, this is typo, is less than or equal to large M for each positive integer n. We already checked it in exercise 9. Here we review again it. Let exercise 9 in section 61. Let a sequence Gn converge to a number G. Show that there exists a positive number large M, such that the inequality absolute value of Gn is less than or equal to large M holds for all M. Okay, to see this, we show the two parts, part A and part B. Part A here, note that there is a positive integer n0, such that absolute value of Gn is equal to absolute value of G plus G n negative G is less than absolute value of G plus 1 whenever n is greater than n0. Okay, to see this statement, we assume let epsilon is equal to 1. Then for this epsilon, there is an n0 which is greater than 0, such that absolute value of Gn negative G is less than epsilon. Here epsilon is 1 if every n is greater than or equal to n0. Okay, this is the definition of convergence. So then let m let m is the result of maximum function which output from among absolute value of g1, absolute value of g2, absolute value of g and 0, and 1 plus absolute value of g, which is the greatest number among them, among here. That is large M. Then we have absolute value of Gn is less than or equal to large M for all, and n is less than n0. Okay? Then absolute value of Gn is less than or equal to absolute value of Gn negative G plus absolute value of G. Because we derive this inequality by using add some which is actually 0. So negative G plus G to this Gn. Then you get this, and then we this part is less than or equal to, and this part. So we get this inequality, and further, Gn absolute value of Gn negative G is less than 1 because this holds. So this part is less than 1 and plus absolute value of G. So we get this inequality, and then by construction of M, which is the output of maximum function of these values. So if n is greater than or equal to n0, then this part is less than or equal to large M. Okay. Hence, we get this inequality, which is absolute value of Gn is less than or equal to large M for all n, natural number. Okay, second part B. To prove this, let Gn is xn plus yn be a convergent sequence. Then each part, the real part and imaginary part, what I mean is xn and yn, the sequence are convergent real sequences. So they are bounded. That is, there are two positive numbers, m1 and m2, as we just checked previous part A. Such that the absolute value of xn is less than or equal to large M1, and absolute value of yn is less than or equal to large M2 for all n. Just let m, which is equal to square root m1 square root plus m2 square root. Then we get this result, desired result. Absolute value of Gn is equal to square root 2 xn square plus yn squared, which is less than or equal to this square root m1 square plus m2 squared, because this condition holds, which is large M. So we have the desired result, which means absolute value of Gn is less than or equal to large M.